Good morning, everyone. My name is Santhosh, and I am here to present our work on MEMS Thermo-Nanomechanical Membrane Flexure device for temperature sensing. It was done under the guidance of Dr. Seena V at Indian Institute of Space Science and Technology, an institution under the Department of Space in Trivandrum. So here's a basic outline of what I'm going to discuss today. First, I'll give a brief introduction to MEMS thermal sensor. Then I'll speak about how MEMS nanomechanical devices can be used for temperature sensing. Then what is a thermo-nanomechanical membrane flexure sensor device? It's a design and simulation, and the different geometries of thermo-nanomechanical sensors, and experimental proof of concept for proving this working of this device, and finally the conclusion and the future scope. So basically, there are different types of thermal sensors available these days, including thermocouple, RTDs, thermistors, bimetallic, and solid-state devices. Each of these devices have their own advantages as well as disadvantages. For example, thermocouple has an advantage of a wide operating range, but it has a low sensitivity. Similarly, a thermistor is of low force, but it has a disadvantage of non-linear curve. So to overcome the disadvantages of each of these devices, we have come up with a new device called MEMS Bimorph thermomechanical sensor. Basically, the principle of thermomechanical sensor is the conversion of temperature change into a microscale motion. These devices have been proved to be useful in environmental monitoring, agriculture, IR radiation sensing, detection of biochemical and lights, etc. So the motivation of this work is the requirement for a linear, high resolution, low cost, fast response temperature sensor. So now how MEMS nanomechanical devices can be used as used for temperature sensing. The answer to this is a Bimorph nanomechanical cantilever, whose principle is the difference in the thermal coefficient of expansion between the two materials. As shown here, whenever there's a difference in the thermal coefficient of expansion between the two layers, whenever there's a temperature change, there will be the tip of the Bimorph will there will be a deflection in the tip of the beam as shown in the equation given here. So one of the layers will have a compressive stress while the other will have a tensile stress. A nanomechanical cantilever sensor is a device which converts any physical or chemical input into a nanomechanical motion, and these devices have several applications such as gas leak detection, medical purposes, process detection, etc. These cantilevers have several advantages such as good sensitivity, low cost, etc. And nanomechanical cantilevers can be used in several modes of operation such as static mode, dynamic mode, and heat mode. In this Bimorph sensor, we have utilized the heat mode of operation for our work. There are several transduction schemes such as optical, capacitive, piezoelectric, and piezoresistive schemes. Among these, the piezoresistive transduction schemes have several advantages such as direct transduction of cantilever deformation into the electrical domain, ease of fabrication, etc. So combining the transduction scheme of piezoresistive, we have to come up with a new architecture. Like for piezoresistive, for getting the maximum sensitivity for piezoresistive sensing, we have to maximize the difference in the longitudinal and transverse stress as given in the equation here. Now consider the two cases of point loading and isotropic stress loading. So in the case of point load, the sensitivity is maximized since the difference between the longitudinal and transverse stress is maximum. While in the case of isotropic surface stress, the difference between the stress components is nearly zero, and hence, in order to maximize sensitivity, we have to use a case of point load. But in this Bimorph cantilever structure, it's minimized. Hence, we have to bring up the new architecture by combining a Bimorph membrane structure with the flexure. So instead of a cantilever, we use a circular Bimorph supported by flexure on 4 of its sides, so that the isotropic stress is converted into uniaxial stress. And this new device is called Thermo-Nanomechanical Membrane Flexure Sensor, or the T-NMF. Now design and simulation. So basically, this is the structure of a T-NMF. Circular membrane, Bimorph membrane is supported by 4 beams on 4 of its sides, and on each of these beams, a resistor is placed, and these resistors are connected in series, and it forms one leg of the Wheatstone bridge. Whenever there's a temperature change, the Bimorph will bend, and due to this, the beams will bend, and this will cause a stress in the piezoresistor, and this will induce a change in the resistance, and this will be measured by the signal conditioning circuit. So based on some literature review, we have found out that aluminum and silicon will have the maximum differences in the thermal coefficient of expansion between the two layers, and hence we chose these two materials for the layers of the membrane. And for the piezoresistive material, we have to get a high gauge factor piezoresistor in order to maximize the sensitivity, and hence we used indium tin oxide as the piezoresistive layer. So this is a cross-sectional view of our device. So basically, the silicon membrane, under the silicon membrane, there will be an aluminum layer, and it will be supported by beams on 4 of its sides. So we have identified that the structure of the beam should be an inverse trapezoidal structure for getting the maximum sensitivity. It will be discussed in the coming slides. So I have told that the aluminum layer will be placed below the silicon layer, and hence, since aluminum has a greater expansion coefficient as compared to silicon, the BIMOF layer will bend downwards, and hence the displacement profile of the BIMOF structure is given in the left side. This is the stress difference profile across the curvature. So as it can be seen that the stress in the BIMOF layer is isotropic, and the stress difference in the along the beams is uniaxial. We can see it in the graphs shown here. So we did a parametric analysis to get the best optimized structure for the NMF device, and we have found that the thinner membrane, the membrane thickness, as the membrane thickness reduces, the sensitivity will increase. Maximum deflection sensitivity was obtained at the thickness ratio. Like we have fixed the thickness of the silicon as 2 micrometer, and for that thickness, we had to find the thickness of aluminum to get the best sensitivity, and we have found that the maximum deflection sensitivity is obtained at the thickness ratio of 0.85. Hence, we fixed the thickness of aluminum as 1.7 micrometer. Now, I had told that we had to fix the geometry of the beam. For that, we varied the dimension W, and on varying that, we have found out that inverse trapezoidal flexure geometry gives the best sensitivity. On varying the beam length, it was found that an increase in beam length decreases the piezoresistive sensitivity. And on finalizing, we have arrived at the membrane and piezoresistor dimensions as shown there. And on analysis of the sensitivity, we have found that the T-NMF structure has a mechanical sensitivity of minus 0.159 micrometer per Kelvin and a temperature sensitivity of minus 0.0107 per Kelvin. It's a delta R by R per change in temperature. And we have done a comparison study of this device with a conventional cantilever architecture and a thermo-nanomechanical trampoline membrane. Also, we have it has been seen in literature review that this trampoline structure had been used for some studies for involving resonance. So we just came up with this idea of comparing the T-NMF structure with the trampoline membrane structure also. So the conventional cantilever sensor had a temperature sensitivity of 0.00638 per Kelvin. The T-NMF device had a temperature sensitivity of minus 0.0107 per Kelvin, and the trampoline structure had a sensitivity of minus 0.0104 per Kelvin. The first two structures, the cantilever and the T-NMF structures, were optimized to get the best sensitivity, but the trampoline structure can still be optimized to get better sensitivity. So that could be carried out as a future work. And we found that the T-NMF structure has a sensitivity about 1.68 times higher than that of the cantilever temperature sensor. So we carried out some experiments for as a proof of concept for studying this sensor. An NMF device had already been fabricated in a lab for carrying out another study related to hydrogen sensing. In this device, actually, a layer of palladium was coated below the silicon layer, but the thickness of the palladium coating was around 20 nanometer. It was really less. So we try to carry out the experiments with this device in order to prove the concept of bending of the BIMOF structure. And this was a device experiment. And we found out that the temperature sensitivity of minus 0.0084 per Kelvin was obtained. Finally, we had found out that a proof of concept of NMF device for temperature sensing with a reduction in resistance with temperature. And a future work of fabricating and testing the T-NMF device could be carried out, and decide optimization of the trampoline sensor could be carried out, and application development for this device also.